Everyone. Well, it's really an honor to be here. I didn't know Professor Johnson, but I have to say, I think it's a really lovely thing to have a symposium in your honor. So thank you for being here today, honoring him, and so giving me this opportunity to tell you a little bit about what we're doing over at WashU. Um, don't worry about digital or sustainable or design or there's some of these words can maybe seem a little scary, but at the end of the day, we're trying to arrange atoms in space so that they can convert sunlight into energy. Okay. And so that's really the crux of what we do is we go onto a computer, place atoms in certain positions, and we compute properties. And over the course of the talk, I'll tell you a little bit about how we do that. But really the devil is in the details here. The important stuff is really the broader scope of how we're actually applying these techniques to solve problems that I find to be very interesting. Do as well. There we go. Okay, so it's very important to note that I am here, I'm giving this talk, but I am one part of a much larger team that does this research. So I just quickly want to acknowledge that there's a bunch of people at WashU doing this work. So there's a Postdoctoral Research Associate, Dr. Manish Kumar, who did a lot of the computational work on this project. There's experimental components to this project. So Professor Ellen Stechel at Arizona State University and her team, consisting of Professor James Miller, Professor Ivan Urbanowski, and Natalia Ali, are all doing the synthetic component and really the fabrication component of this project. And then the final component of this is at Ohio State University, where they're actually doing what's called a techno-economic analysis. The idea here being that we are theorists, so we come up with new materials. The synthetic folks at Arizona State try to make the materials and characterize them. So whatever property we care about, they try to measure it for us. And then our friends at Ohio State, they take everything into consideration. They try to say, well, how much do these materials cost? How much would it take to build this reactor? What are the labor costs? All of these different things to give us an estimate as to whether or not this will ever be commercially feasible. So it takes a team to design a material that actually upends an industry. And fortunately, we've got such a team. And hopefully, we'll be able to make some impact in this area. And before I start, I don't know if it's typical to have questions during the talk, but I'm perfectly fine with that if that's okay. So if you have a question during the talk, please feel free to just raise your hand and ask me, okay? All right. So the first slide is really just trying to emphasize that most of our energy comes from fossil fuels. And we have an abundance here in the United States, which is really fortunate because it's a great thing to rely on. But as I'll show you in a moment, sun actually provides so many times the energy that we actually need on a momentary basis that it's just tantalizing to think, can we convert just a fraction of that, have all of our energy supplied? So regardless of how you feel about different sources of fuel, the sun really does possess quite an amazing amount of energy that we could harness. Can we actually harness that? What are the different pathways of doing that? I'm going to show you one of them today, but there are many. So here you can see the gray boxes. That's all of the different fossil fuel sources of energy. And then down in the right corner, you see some of the renewable and sustainable forms of energy. So we have biomass, wind energy, hydro energy, so like water, like dams and stuff like that. Then we have other. So somewhere within other is solar. So can we make solar a larger component of this and actually harness some of that energy that hits us on a daily basis? And one of the reasons for doing this, not only just an energy security reason, we have more than enough energy in the sun to do everything we want to do and more, but we also have an issue in the sense that temperature on the globe is rising, and there's certainly good evidence to suggest that it's due to what we're doing, and it's due to burning fossil fuels. And so lessening reliance on that, not just from an energy security standpoint, but also lessening global warming and the effects of that, it's a win-win. So that's why I'm working on this problem. And I should mention that while I'm a theoretical chemist, I was telling Gifty this earlier, that I do everything on a computer. I model things, and that's really, I guess it's kind of like a gamer mentality that we can kind of put things in place and we can see how they evolve in time. And there are equations from physics that tell us basically how things should, pan out in the simulation. And that's really fun. And I could probably just do that and enjoy my career. But our group specifically, we're very focused on, can we apply that and do something meaningful? And so we're taking this kind of gamer mentality and trying to apply it to designing materials for different processes. So here I'm showing you the promise of solar power. So we have the sun, it's hitting our Earth. There's an atmosphere surrounding the Earth. That atmosphere will actually absorb some of the power density that's hitting Earth. So there you have 1,361 watts per meter squared. Watts is a measure of power. Power is a measure of how much energy are you giving me every second. Then if you divide it by distance squared, you get how much energy are we getting per second on a square meter of Earth, okay? So what happens is that energy that's coming from the sun, some of it gets absorbed. About 361 watts per meter squared gets absorbed. We still have a great deal of it. And that eventually gets down to the Earth. So the question might be, how much energy is that compared to something we might need to power? Here I'm showing a house. It might be a house somewhere in Missouri, which I've attempted to outline with my little box there. And that house has a square area of a square footage of 255 meters squared. It needs, on a momentary basis, so energy per unit time, 1,223 watts. Solar power on that little patch of land, if you were to just take 1,000, is how much energy is hitting a square meter, and multiply it by the square footage of that house, you get 225,000 watts hitting your house. You only need 1,200. There's a lot of energy that could be harnessed. Okay, so how could we harness that energy? Well, one way to do so is to create what are called solar fuels. A solar fuel is something where we essentially are taking that energy from sunlight, turning it into chemical energy. And for us, the chemical energy we like to generate is hydrogen. Hydrogen doesn't just exist as H2 typically in our environment. Typically, we have water in abundance in our environment, and that water could be converted to H2 by splitting it. So goal is in solar hydrogen production to split water molecules to form hydrogen gas and oxygen gas using that energy that's hitting that square meter on Earth, okay? The current way we do it is by a process called steam methane reforming, where we take methane, we react it with steam at high temperatures. And what happens is we form some H2 and we actually form some carbon monoxide, which obviously is problematic. So they actually then take that carbon monoxide, react it with more water, and they can create more hydrogen gas, but they then create carbon dioxide. So at least it won't kill you, but it might kill you later if the global warming continues at the rate it's at. So steam methane reforming is a contributor to greenhouse gas emissions. And so is there another way that we could produce this hydrogen that is so important to us? It's used in pharmaceuticals, it's used in plastics, it's used in the synthesis of all sorts of types of resins and cosmetics. It's really the way of, it's one of the many ways of manipulating organic molecules is using hydrogen as one of the reactants in some chemical reaction. So we need hydrogen really badly. In addition to the fact that we could use it in all these different industrial processes, if we react it with oxygen, it actually releases a ton of energy. And that was the problem with that Hindenburg balloon, that they filled that with hydrogen. And that kept it floating in air because hydrogen is less dense than air. What happened is that there was a spark, and that spark allowed a reaction to occur with the hydrogen in the balloon and the oxygen in air. It formed a lot of water, a gigantic explosion. So there's a ton of energy stored in hydrogen gas. So can we produce it? And more so, can we produce it renewably and sustainably? One way to do this is through what's called photoelectrochemistry. Write that down. Photo, that means there's photons. That's like sunlight, the ultraviolet visible waves that are coming from the sun. We could use those. We can excite electrons, and those electrons basically can jump off of a bond and through a circuit And what will happen is you basically break bonds that way. Another way of doing this is the way that we actually do it, is through a process called solar thermochemical, or here I'm showing concentrated solar energy. So concentrated solar takes a different approach. Instead of using the wavelengths of light to excite electrons, what it does is it actually collects solar wavelengths, concentrates them in a point in space. What happens, just like the magnifying glass that concentrates sunlight and causes the leaf to set on fire on your sidewalk at home. Maybe you did that as a kid. Maybe you're not me. But that process of concentrating sunlight to create heat, we can do that on a huge scale out in the Arizona desert. So that's showing at the National Renewable Energy Lab. They have all these mirrors set up, and these mirrors collect the sunlight. And at the top of that tower at the bottom, it creates temperatures that are just ridiculously hot. Talking like thousands of Fahrenheit, like 2000 Fahrenheit. Really incredible. So why might we choose one process over the other? Well, at least steam methane reforming, that middle process, it produces hydrogen at a cost of $1.8 per kilogram. So while you may not have a great sense as to whether or not that's economical, this is the standard process. So at the very least, if we're going to produce a new process for creating hydrogen, one based on solar, it should have a dollar figure that's lower than steam methane reforming. In fact, it should be much lower. Otherwise, we're going to be hard pressed for an industry to decide just to abandon the current process they're using. It costs a lot of money to run a plant like that. They don't just want to shut it down. So you have to give them not just a price point that they would have gotten from their original plant. You have to give them more than that. So the goal is to really be lower than that 1.8. Photoelectrochemical, where you're exciting electrons to break water molecules. This can reach somewhere around $2 per kilogram. Problem with this process is that the materials that are used to actually absorb the sunlight and to actually split the water molecules, they tend to degrade over time. So while you can reach $2 per kilogram for a certain amount of time, you have to replace those materials fairly frequently. It's really not a great solution at the moment. Last process, what I'm studying, you might see $4 to $6. Why even bother? Well, that's why we're bothering, because we think that there are ways that we could probably lower that. So the aim of what we do is we're trying to design the materials that are really crucial for this process. And we're trying to find materials that are based on cheaper elements that allow for more cheap synthesis and scalability. So we can actually get to the point where we're putting, we're creating a process in one of these concentrated solar plants. Okay. So before I get into the specifics of how do we design a material, so how do we actually create a new crystal that has atoms arranged in a particular way that are perfect for absorbing the sunlight or absorbing the heat from the concentrated solar plant? Well, first I'm going to tell you a little bit about materials design and what the process is like. So the analog materials design, this is kind of how it's been done in the past, okay? So typically what's happened is that at a lab, maybe a company or a national lab or maybe even an academic research group, you hypothesize a material, you come up with something. Maybe you just did an experiment, off the cuff and you got a great result. Or maybe it was building on something over time, but you come to some hypothesis as to a material that might work for this process, okay? This is just a generic material. This really kind of applies to anything. So to hypothesize a material, what you really need and what some of your main costs are, personnel. Reason that is because at this point, you're not really making a lot of material. And so you don't need a ton of all these other things. However, you get to the point where you need to make the material and make it, in bulk. Now we're talking about a lot of costs coming from different things. You need personnel to make the materials, you need materials, so you need to actually get precursors or reactants that you can heat up and will make the material that you want. You need equipment, you need synthetic equipment, you need characterization equipment, you need it all because you not only need to make something, you need to actually show that it does what you're intending it for it to do. Then you need space and you need it all. So it can be very costly at this point in the process. And then, of course, what could happen is you try to make this material you hypothesize, and it doesn't actually get made. Now you've spent a lot of money. Okay, but maybe you try to make it, and you actually get the material that you intended to make. You try to characterize it. You're not going to need to get any more materials because now you have that material, but you still need to pay for the other things. You need personnel who are going to characterize it, who are going to do some experiment to probe its properties. You still need a lot of equipment. You might need new equipment. You need space, maybe even more space, because now you've got all these characterization instruments in your lab. Okay. Then what might happen? Well, you were able to make the material, but you found out that its preliminary properties were suboptimal. Okay, so our hypothesis, we hypothesized something that could be made, but it didn't actually do what we wanted it to do. All right, restart. We can keep doing this, right? Then you make the material, you characterize, and at least in the lab, it looks good. Now you have to fabricate a device that's actually going to cause the process to go. This is another huge step in the process. What happens if you try to put the material into the device, right? What if there's a predetermined design for the reactor that we need to work with, right? What if we can't get the material to adequately integrate with that material or with that reactor? That's problematic, but there's really not much we can do, even if the material is great. So we could make a new reactor. Actually, we do that. But this is a failure point for a lot of people as well. So now we go back to the beginning. Then, we might be able to fabricate the device, but then we test it and we're like, well, it doesn't actually do that well for the process. So you can imagine, like if we're doing this in a lab and we're trying to make these materials and we're trying to characterize them and all this, it could take many years and you might not actually make anything worth implementing in, or anything that anyone would invest in to make it a commercial enterprise. Moreover, people don't really publish bad results. So we don't even know. So I might come around later and someone might have done all of this and I might come around and say, I'm going to try this material, and then go through this whole loop only to come to the same conclusion someone else came to. Lost a lot of money, a lot of energy. How do we make this better? This is where we come in. So we do computation, we do simulation, and we're trying to design materials. So here I'm showing different candidate materials. So here are each of these spheres is an atom. The colors indicate the element, and you can see there are different colors here. They're arranged in different ways, and this is really the complexity that exists in crystals and in solid state materials. You have these atoms arranging in like really intricate and beautiful ways, and the way that they arrange and the particular amounts of the different species plays a huge role on their properties. So we can come up with these candidates. And in fact, there's existing databases where you can today log in and see breadth of complexity that exists in materials. Okay, Materials Project is a great example of this. So anyway, so what we can do is we can say, well, we know how much the elements cost. If you were to go to market and try to buy platinum, it's really expensive. Or if we're trying to make something and we know it has a particular precursor that we need, so some particular molecule that's a great starting point for making the thing we want to make, well, we might be able to say, oh, that's expensive, that's not expensive. So we can actually filter on that. Then we ask a question, is the material stable? So that's answering the question of, can we make it, basically? Because if it's not stable, even if we try to put things together, it'll just fall apart. So we can ask that question. Then, once we've asked, is the material stable, we can ask, is the property that we care about in the right range for the process? So the process might have a particular value of the property that we need. We can try to compute that property and see whether or not we fall in that range. So we can do all of this on a computer, and we can use concepts from quantum mechanics, thermodynamics, kinetics, and combining those together, we can make these predictions, and we can say, well, at least on a computer, these materials seem worth synthesizing. So you can imagine, instead of doing that loop, that costly loop 1,000 times, maybe we do it 10 times now on a set of materials that are, at least from a computational standpoint, at least on the basis of chemical physics, seem reasonable to investigate. How do we actually do that? So These are words, but eventually everything has to be written into a computer program. Those computer programs are then run on a variety of different machines. When we're getting started, we usually have like a little server that sits in my office, and I can tell when everyone is working on things because the fan starts to run and I can barely hear myself think. Then there's what's over there called the RIS. This is like a university resource. So universities will sometimes invest in their the computing resource that people can access. And then there's Kestrel. This is the machine that we're using for really the heavy duty stuff. So this has so if you think about your like a Mac computer or a regular, regular PC, that's maybe quad core. That's like a pretty typical number of processors on your computer. This has hundreds of thousands of cores. So we're talking like 25,000 laptops worth of power there. It's really kind of incredible. And it enables a lot of the really complicated calculations that we need to do. So when we're doing this process, not only do we need computational support, but we also need to know what properties are we calculating? How are we actually going to determine whether or not these materials are plausible? Well, if we want to know prices, we can look at the periodic table. There's well-known price points for things. If we want to know stability, if you remember phase diagrams from general chemistry, if you increase the pressure on water, it'll turn into ice. Depends on where you're in the phase diagram. If you decrease the pressure on water, it'll form, vapor. If you heat water, it'll form vapor. So we know that under different conditions, different phases might be stable. We can do the same thing with complicated materials, and we can say, if we combine these elements together in this particular ratio, should they make something? That's what we're asking. And then days to months later, instead of years later, we come up with a few promising candidates. So ultimately, this can really reduce the number of cycles we need to take. Okay, so once we have a bunch of materials, we can compute. I kind of drew this like baseball cards because I collected baseball cards growing up. And you have the different materials, you have their stats, and each of them has like some property 1, 2, 3, and maybe property 1 is stability, property 2 is the reactivity, stuff like that. And then what can you do? You can build an Excel sheet. In an Excel sheet, you list all these properties out, and then you go to your favorite form of either linear regression. You can go in Excel and fit a line, which is actually pretty much what we were able to do in our study, or you can do something more fancy like a deep neural net to try to learn how properties 1, 2, and 3 map to the promising, some property that we care about, and ultimately determine whether or not something will be promising or not promising on that basis. So the machine learning kind of stuff is just a way of learning the things that we are, just by looking at this data table, can't learn ourselves. And so it finds hidden correlations, and it's able to push us in the right direction of what might be worth making. Okay. Back to concentrated solar and solar thermochemical hydrogen. So how does this actually work? Well, the way that it worked is that you have sunlight hitting these mirrors. When the sunlight hits these mirrors, basically, depending upon just the architecture of the mirror part of this plant, you can get like thousands of suns worth of solar intensity. And what that can do is that can basically give you really high temperatures. What you're creating is essentially an oven. And what could you do? Well, you can cook something in your oven. And what is our idea? Well, our idea is that what if we try to split water by cooking? I've said this before in talks, and I kind of like regretted it, but it's kind of funny. We cook rocks. We basically take rocks from the earth, which are oxides. They have metals, they have oxygen. We cook them at high temperatures. What happens is they release some of their oxygen that are in. Okay, we'll talk about that on the next slide. But the way to think about this too is that there is also efficiencies we have to care about. Okay, so there's one efficiency that is basically the hotter a material gets, the more energy it actually lets off. So if we're thinking about heating this material, if we go to too high of a temperature, it'll actually what's called re-radiate its energy. And so that's basically like if you see something glowing, it's re-radiating energy that's heating it. So actually it won't get as hot as you might think it gets because that energy is coming off of it. It has to come off. Then there's also this, what's it called, efficiency that works in the opposite direction. That as you go to higher temperatures, you actually are making your process more efficient. And this is definitely the least favorite topic in the thermodynamics course I teach, but it's this idea of what's called the Carnot efficiency that says basically the hotter the oven, the colder the kitchen, the more efficient the cooking is. Okay. So the higher we go in temperature compared to our external surroundings, which are ambient temperature, the more efficient this process gets. You've got two competing efficiencies, which say that, say you were to work with this particular solar power tower station, you could basically get about 80% efficient conversion of that solar energy into energy that could do the chemical work of water splitting. Which isn't bad, actually. That's quite a bit of that, right? Because I told you before, we needed 225,000 watts to, that's how much was actually hitting our house. We only need 1,200. 80% of 200,000 is still way more than enough, right? So that's not a problem, actually. This is for a specific architecture where the intensity of sunlight is 10,000 suns. Okay, so I haven't mentioned how I actually split water yet. The most naive way of splitting water is just to say, well, you have all this concentrated sunlight. Let's just like put some water in there, right? And the water will heat up and it will vaporize. And actually, it's so hot that it will not just vaporize; it will turn into hydrogen atoms, oxygen atoms, OH groups. So that's actually not so good because we wanted H2, but it's so hot that actually what ends up happening is everything else starts forming too. So we get a mix of things. It's hard to separate, and then it's just not as practical as we might have hoped. The alternative, however, to just splitting water molecules that are just in the air is to use a material that can act kind of as a template for where that process occurs. So consider this for a second. This is a two-step cycle, and you start out with MOX. MOX this is my rock. It's a metal and it's an oxygen. X just means there's some amount of oxygen in there compared to the metal. Okay, it's the ratio. What happens if I heat it up? When I heat this material up, it tends to release some of its oxygen. Okay, so what you end up with is MOX minus delta, where delta is this amount of oxygen that got lost, that went off into the atmosphere. What would happen though if I cooled the system down? What happens is that once I cool the system down, it says, well, I only wanted to get rid of my oxygen because I was hot. Now I'm cold. I'd like my oxygen back. So that creates a scenario where if we present it with a source of oxygen, and that source of oxygen is water, it is going to rip oxygen so dramatically out of water that we can very efficiently form hydrogen gas, and only hydrogen gas. It's not going to form some other thing like hydrogen atoms, which that's problematic. So we'll actually get hydrogen gas, and then that oxygen that came from water, it makes our metal oxide again. Our rock is back to its original form. You just keep doing this. And actually, because they're rocks, right, they exist on Earth and they've stood the test of time. They're stable. You could heat them up. Volcanoes will erupt, and these planets will form, and these rocks will still be here. Okay, so if we can just find ways of kind of knocking some of the oxygen out and replenishing it through water, then we have a way of producing hydrogen from water using this solar heat, which is basically doing the heating part. The next. So there's a lot of different types of materials that could do this process, and I'm not going to talk about all of them. There's different ways to skin this cat. Ultimately, the materials that we're going to use are called perovskites. And why perovskites? Well, good question. Because they're really cool looking, number one, probably most important, but also they have a really unique structure that I'll tell you about in a moment. So first, I want to just refresh you that last slide I said we have a metal oxide. It is just metal and oxygen forming a crystal. Heat it up, it loses oxygen, we replenish it. You could have, instead of just a single metal and oxygen, you could have two metals and oxygen forming some crystal. And that's what a perovskite is, at least in its most basic form. And we do this process. Heat it up, lose oxygen, pull it down, give it water, it reoxidizes. Keep doing the cycle. And that's the thermal reduction and water splitting step. Now, how do we increase the amount of hydrogen we can make? Well, we design materials that can release more oxygen when they're heated up. Because if they release a lot of oxygen and then present it with water, like give me all that oxygen, right? So the better it is if it can actually release a lot of oxygen when it's heated up. And basically the amount of this delta or amount of this oxygen that gets lost from the material when it's heated up is going to be related to the free energy to form defect in this crystal. And what do I mean by that? There's going to be some energy requirement that knock an atom out of the system. Okay. And that's what that little EV in the box over there is. Our goal is really going to be to compute that quantity. How much energy is required to knock an atom out of the lattice? If we can compute that, we actually can do design on this process. So here's showing this perovskite structure. I told you it's a cool looking structure. Think about a box, and at each corner of the box, you have what's called an A site. A site tends to be a bigger cation, so it has positive charge, and it sits around a B site, which is another cation. So it's another thing that loses electrons. And these are arranged and connected by oxygens. You've got yellow A sites. You've got this purple blue B site that actually connects with oxygens to form this really beautiful octahedron at the center of the box. And then you've got connected to it these different oxygens. What I've depicted with that little dashed black circle is that we're trying to remove oxygens from here. So that's basically the process we're trying to do. Is can we predict how much energy is required to make that little vacant site? And also we can imagine looking at any number of elements in the chemist's palette. So we can just go to our periodic table and we can say, well, what do we want to put on each site? And we don't actually have to conform to what can be made in the lab. We can put them all together. Sometimes they won't be stable. Sometimes they will be stable. We can contrive any experiment that we'd like to do on a computer, ultimately to try to find things that will give us the right value of that energy, EV, that is required to knock an atom out of the lattice. Okay. More than that, though, these calculations to compute that quantity, they rely on quantum mechanics. Just as scary as the word or the calculations, really expensive. We need that Kestrel supercomputer with, tens of thousands of laptops worth of power to actually compute that quantity. So it'd be really nice if we could find some simple way of doing that. And it turns out that there's, a simple way of thinking about this. If you have some set of cations or positively charged metals, they've lost their electrons, and those electrons have gone to an oxygen because oxygen likes to get electrons. You can imagine the process of knocking an atom out of the lattice as follows. First step is the energy required to pull out a neutral oxygen atom and leave its electrons behind. Okay? Details of that, maybe not worth emphasizing too much, but there's basically one step of this is thinking about if you were to just cut the bonds and let the electrons go back to the metals, right? What would be the energy released when you cut the bonds? If you pull a rubber band and you cut it, it snaps back. What was that energy stored between the positively charged cations and the oxygen that's there? There's this first energy. So you can imagine energy goes up. You need to supply energy to make this happen. It's like trying to rip the phone book. How much heat do we need to actually tear it in half? And the second step is what's called crystal reduction. So here, this is a little bit harder to think about, but if you pull out an oxygen gas and it's going to be neutral, you're in effect leaving electrons behind. Electrons are going to have to go back somewhere. What are they going to do? They're going to find atoms nearby. They're going to what's called reduce cations. It's called reduction because the charge on them, what once was 4 plus becomes 3 plus. Okay, and so electrons need to find new homes. So there's the bond breaking energy and the stabilization associated with the electrons saying, well, I'll go find a new home. And the ultimate reduction of that leaves us at a new green line. The difference between the initial and final point is the energy of this process. So we can build a very simple model based on this. So we basically build a model that encodes these pieces of information. We calculate that quantity. We actually do a bunch of brutal calculations of this energy required to knock the atom out using initials there are DFT. This is just one way of doing quantum mechanics on the system. And what we find is that Well, actually, we can write down a very simple linear equation. So it's just a bunch of slopes and intercepts. And we can write down some equation that can basically fit that. So this complex quantum mechanical problem, what it's saying is that you can boil it down to fitting a line in Excel. And that's what we did. So why does that matter, though? Number one, if we are able to build a model like this, it tells us that our intuition is actually pretty spot on. So this idea of thinking about bond breaking and reduction actually, bears fruit. But another important thing is that if it's pretty accurate, then I don't have to do a calculation anymore. Why do these calculations on that huge supercomputer if I can, with the snap of a finger, look at like a million materials? Because how easy is it to use a linear equation? You just plug a number in, compared to the quantum mechanics, which we don't even need to talk about. It's much more complicated. So if we can fit everything to a simple model, then we can scan really quickly. That's really important. What does it tell us? Well, it tells us a few intuitive things as well. It tells us that we want to avoid cations, these A or B sites in the crystal. We want to avoid ones that form too strong a bond with oxygen, as if it forms a strong bond, it's hard to break it. We want metals that actually are more reducible. So you, in a sense, you want metals that, if you were to break that bond, are really happy to receive an electron or don't mind it so much. We also need some other features. The last feature there is related to stability. It actually turns out if you are less stable, you're more predisposed to form missing atom defects in your crystal, because that's one mechanism by which a material decomposes. So all of these things tell us something. We can compute these all. In fact, all of these different features, bond strength, reducibility, stability, I can look that up in a thermochemistry data reference. So I don't have to do a calculation. I can just go to the library or search the web and find the particular values I need, make a prediction, and it's always going to be pretty close. Okay, not going to talk about entropy. But we use this and we said, let's find elements that we can put on this A site and this B site that have the right properties. And what we found was actually that if you put calcium and cerium on that A site, that box corner site, and then you put manganese, and later on we find titanium on that other site that has that nice octahedral arrangement of oxygens around it, this material is predicted to be stable. So we do a calculation, it doesn't break down. And if we actually compute the energy required to knock that atom out, wow, it's like right in the range. Here's what it looks like. This was a model we came up with. So here the green are cerium. Those green circles are cerium. The blue is calcium. The gray octahedra are titanium surrounded by 6 oxygen. And the purple are going to be manganese surrounded by 6 oxygen. You can see diversity of color. It's basically like kind of a random mixture of these species on their respective sites. We created this model. It appeared to be stable. Our predictions was that it was stable, and our prediction was that it could form these oxygen defects. The atom could be knocked out with just the right energy to really be effective for this process. So the first thing you test is whether or not you can make what we predict. And basically this plot on the right here is the result of just scattering a bunch of X-rays off a material. And what's really neat about it is you can actually, based on the X-rays that bounce off, you can process that, and you can reconstitute where the atoms were in the crystal. We can compare that against our crystal. It matches almost perfectly. So it's tough to see, but if you actually track the blue data points and the red curve, blue is experiment, red is theory, or what we predicted, it matches almost perfectly. So number one, it can be made. Number two aspect is, well, can it actually form these defects with the right energy process? The way we think about that is by thinking about, well, if there's an oxygen and you can see there, it's turned black, that means it's now a vacancy or it's now a missing atom. So if you calculate all the features associated with different environments, you can ultimately make predictions on this value depending on which oxygen you are in the crystal. As you can imagine, based on the fact that there's like a mixture here, you might have different oxygens that are kind of in different environments. So one oxygen might be like, yeah, I don't mind leaving because this environment is terrible, right? I don't like being here. But then other oxygens might find a very stable environment in this kind of random crystal. So there's going to be a little bit of a spread of this value, this energy that's required. But on average, it's right where we need it to be. And in fact, if you go and do an experiment here, this shows the black line right there is temperature that's being imposed on the sample. So you can see there's every once in a while, there's a big spike, basically like a big rectangle that comes up. That's a big heating cycle. Okay. You can see when you heat it at around, say, 500 seconds, you see a big red peak. That red peak is the oxygen coming on. We can actually measure that. Then you can see in the next part of the cycle, the oxygen, the red kind of tails off, and we see a new thing emerge. What happens in between the red and the blue is that we cooled it off, we presented it with water, and we saw a new peak. And that new peak was related to hydrogen. So you can actually compute the area under that curve, and that tells you how much hydrogen you were able to make by basically producing these missing atoms and replenishing them by splitting water. And we were able to make a certain amount that actually, if you compare it to the other materials that are used for this process, it's better than all of them. And what was kind of crazy is that this was only one possible, ratio of these 4 different metals that we put in this crystal structure. Okay, so you can imagine there's all sorts of possibilities. There's this X, this graph right here shows the amount of cerium versus calcium. The Y is the amount of manganese versus titanium. I only looked at a point. Like you could go a bunch of other places. Can we find better materials? And so this was the subject of the current work we're doing that the Department of Energy is funding. And it's also funding the building of a reactor. So I'll talk about that a little bit. How am I doing on time, by the way? Okay, perfect. So thus far, I've showed you we can, to try to circumvent this cycle, this costly cycle of experimentally designing materials, we can do calculations of a few properties, make a set of predictions and say, can you try making these 10 things instead of them just trying, our experimental colleagues making maybe 1,000 or 10,000 different things, okay? And we came up with something that they were able to make, and they tested it, and the property associated with its ability to lose oxygen from the crystal, it panned out. So this was really exciting. It kind of suggested that this was, a really good system for which we could basically proceed experiment and try to identify new ratios of the calcium and cerium on that one site and titanium and manganese. So we looked at a few different compositions. You can see here the X is just XCE, is just how much cerium is there compared to calcium. So 0.25 just means 25% of the sites on that crystal have a cerium on it, 75% have calcium. And it's the same type of thing for manganese and titanium. We looked at a bunch of different compositions. We can calculate actually an energy quantity that is related to the material's ability to decompose. The larger the number, actually the less stable the material is. This is going to be related to how much heat is released when it actually decomposes. And we could determine which of these were stable or metastable, which of them were really unstable. What we found was if you know a little bit about these materials, this range of metastabilities or of decomposition energies are all pretty reasonable to expect to be, be able to be made in a lab. So the first thing that this suggested was if we move around in this composition space and try to make a better material, it's probably not going to affect stability that much. So that's really nice, actually. And another thing that we can do is because we can compute the energy required to remove these oxygen atoms from the crystal, we can do it for all these different compositions. We ended up generating a whole new data set. We used that model that I told you, that linear model, fit it. And what we found is, this model works here as well. So what's great about that is we can do these 6 compositions, but then the infinity of compositions you can imagine in that previous plot. So back. The infinity amount of compositions you could imagine in this square grid. We can just now make a prediction using that model, which is like snap of a finger. Whereas before, it would have required a lot of brutal quantum mechanics calculations. So that was a really important finding for us. So we built that, and it identified that these materials have the energy required to form that oxygen vacancy. It's right in the sweet spot. So What did we do? We went to our experimental colleagues. So this is Natalia. She's at ASU, Arizona State, and she's, you know, you see the results. You don't. The process is arduous. She went through a lot of different trials and tribulations to design, to be actually able to make these materials, but ultimately she was able to make a number of these different compositions with more on the way. What we found is that actually all of these things are stable. So we can make all of them. We can get all the different compositions that we simulated on the computer. They made different batches. So you can see here on the right, this shows these materials being made. It's made through a process that's kind of like a solution phase process. It's kind of like a liquidy goop. You heat it up and it reacts and the atoms rearrange to form our crystal. Then it forms what has been, I think, fairly accurately described as the souffle, which is when it's been dried. So this is the material after it's finished cooking. And we dry it off. We do a process called calcination. Calcination basically means that we heat it to high temperature. And what happens is there's enough energy for the atoms to kind of like jiggle around and fall into better spots, like spots where they form more bonds with other atoms. So it's a way of kind of nudging the atoms into their ideal situation in the crystal. Then we press pellets. So you can see the transformation. You go from like almost looks like an uncooked egg to a pellet. It's black. We then do a process called sintering. Sintering further refines the structure. We end up with a material that's really well ordered, has the right composition, and is ready to be characterized. So the first thing we'll characterize is, again, the structure. We'll shoot our X-rays at the material. The X-rays will bounce back. We'll process where they got shot. Hopefully they didn't hit us. And we will create a graph. Basically, that little theta there is an angle. So if you shoot the X-ray on the material, where does it bounce off? Measure the angle. By measuring the angle, you can actually reconstitute the structure. So here I'm kind of color coding it that she measured this pattern of X-ray scattering off of a bunch of different materials. And if you actually compare those to our predictions of the structure, they match almost perfectly. She then went ahead and took those compositions and did a process called thermogravimetric analysis, TGA. TGA basically is it's an oven that can measure the amount of mass produced by a system. So if you were to put like an ice cube in a TGA and heat it up, you would eventually see the mass of your sample decreasing and decreasing until mass is zero. So all the water is vaporized and it's no longer in the capsule or it's in the vessel that's kind of holding it. So TGA can tell you how does the mass change as you heat the system up. The mass is going to change when basically things vaporize. So this is kind of the precursor to a better experiment that we'll ultimately do. But if you look again, this shows in the red is temperature. So we're doing a process where basically we ramp up the temperature. That's like 1200 Celsius. So we're talking like 1500, 1600, something like that Fahrenheit. And you ramp up that temperature. And what happens? Well, you see the black curve. It rises up. And that black curve is how much oxygen has been driven off of the material. Okay. So we can measure as a function of time and temperature how much oxygen we're able to drive off. So what do we care about here? What we want to see is that black peak go really high. As the higher that black peak goes, the more oxygen we were able to drive off. But also what we want to see is that if we do this again and again and again and again, we see basically the same thing happening. That means that the material is undergoing a change. It's essentially reacquiring oxygen from water and becoming what it once was, basically back to its initial state. And then we do it again. And if it never decomposes, then we're in business. So this is really a promising sign. And this was for one of the particular materials that we're really excited about. Wouldn't have been possible without us working on a computer, just because while we had calcium, cerium, titanium, and manganese, and that was a complicated problem to determine what the good ratios are for that. Everyone else is working with even less information. The whole periodic table. How do I put things together? At least we were able to identify a tangible path to success that ultimately bore fruit. What's really cool about working with engineers, I'm a chemist myself, so I just think about the atoms and the molecules and stuff. But they think about, well, actually, how do you get this into a process that will work? you actually have to take the material and you have to turn it into something that's going to be in the reactor. So for us, we have a reactor. And the way that they wanted to do this was to create a bunch of little discs and to hang these discs, or basically put these discs on a line. And why that's good is because a disc is going to have high surface area. So there's going to be a lot of a lot of regions where oxygen could be exchanged, with water, or it could leave the crystal. Basically, the more surface you have, the easier it's going to be for the oxygen to leave the crystal. So we wanted something that had this high surface area, but we wanted to also pack it fairly densely. So a disc was a pretty natural choice. Believe it or not, what we can do these days is we can 3D print a mold, and then we can take the material, we can basically press it into the mold and form this disc. So I think this is amazing. But we can make these like very complicated, they call them form factors. We could turn it into little triangles that stack, or we could make little cubes, like, I don't know, like a few cubes of cheese on a toothpick or something. We could do really almost anything, because we can 3D print a mold and we can press it into the mold and the material holds up. So we create this disc, and then we put them on a conveyor belt. So you can see. So you can see there on the right, that's the reactor, or at least that's what would be that's the guts of the reactor. And you have these materials kind of moving around the reactor. And at certain points, they're exposed to this concentrated sunlight. They heat up and they lose oxygen. But at other points in the reactor, it's cold, and actually there's a source of water. So it's a continuous process. And actually this makes it more efficient too, because we can take any heat that might be lost from the material and try to repurpose it. And if we can do that, then we increase efficiency. Okay, so with that, I want to kind of summarize where we've come, and I'm happy to answer any questions. I see there weren't any. Hopefully I didn't miss a hand, but we want to design new materials to make new fuels. And while hydrogen can be made pretty efficiently through a fossil fuel-based process, there's so much solar energy, and there's means by which we could potentially harness it that it's, I think, tantalizing to explore. So what we did was we circumvented kind of the old way of doing things, of mixing a bunch of things, heating them up and trying to characterize them and hopefully landing on something that worked, and to use fundamental chemical physics that we learn in graduate school to try to predict, the properties of these materials before we would even make them. So we did that, and they suggested materials that should work. They did work. And they were, beyond what we could actually even predict. They were able to form into the right shapes that we would want to integrate in a reactor. We ultimately have reactor almost in place to do this process. So it's really been just a wonderful experience to work on a project like this, because what I do sometimes feels like it's very far from end user. I'm working on a computer, I'm gaming, as I said before, and am I actually doing anything to contribute to society? This makes me feel like, there's something that can be done, and there's so much left to explore, and we can only do a small piece of it. So hopefully this has been inspiring to some of you. There's a lot of opportunities out there, not just in a lab, but also behind a computer, and even more so in the coming ages, in the coming days, that with all the new technology that's emerging, there's going to be the possibility to solve huge problems like this. And while we're not sure if this is really going to completely do the trick, at least shows all the signs that it's worth pursuing. So anyways, I just want to thank you for your time. And thank you again for the honor for giving this lecture, and happy to take any questions that you have. Yep. Yeah. Over here. I like this. Should ask Elon Musk. I don't know. So the solar, there's different types of solar utilization. Solar panels are probably what you're most familiar with. Solar panels, you can make them pretty efficient, but you would need to power the United States would basically be the size of like 2 medium-sized states of the US completely covered with solar panels. But then you're also not accounting for things like cloud cover and stuff like that. There's a lot of complexity. For this, if you could produce hydrogen this way at a cost-effective, at that $1 per kilogram clip that we're trying to aim for, you could upend the steam methane reforming industry. You could actually get this to a point where a business person would hear this plan and say, I'm willing to invest money in this. You really need to outperform industry in order to get people behind this. So I don't know when it'll happen, but there's a lot of research that still needs to be done. And so I would say that this is showing signs that it could edge towards that efficiency regime that's necessary. Solar panels, I think silicon is an entrenched technology. There are other people trying to come up with new materials, but the problem is that these materials have other detrimental properties that silicon doesn't have. And also there's an industry built around silicon. So I don't know when. I hope soon, but there's so much energy to be had that I think as long as we have good people working towards it, eventually we'll get there. So I don't have a number for you. My guess is on the order of decades, not centuries.
Any more questions? What got you excited in this project?
Well, what got me excited was, so I started out with the fundamentals, that model I showed you that be built on an Excel sheet. That was really cool to me because I want to think about things and I want to have a picture in my mind as to why it might be good for this process. What really got me excited was when we said, well, this model should work and it should be able to help us find a good material. And then it actually made a good. And I think seeing the things that you come up with on a computer, not only does it help you, trust your intuition about things, but it also, it really does suggest that there's this, real opportunity to make things on a computer. And I think that's what I love about it. I get to combine two things that I love, putting atoms together in different arrangements and trying to contribute to society. So that's what we do in my group. We try to find all different ways that we can do that.
Thank you so much
You're
for
welcome.
coming.
Thank you.